Okay, we will start now. So today we basically start with doing some derivative and some theorems we will do like the Rolle's theorem, mean value theorem, etc. We'll do some application. So let's start with a basic differentiation now. So you have two differentiable function here, f and g you have. Okay, we'll just close the week too. Okay, such that what you know is f of 0 is 0, g of 0 is 2. Okay, and you know the f prime at 0 and g prime at 0. Okay, so you don't know what the function is, but you know what is the function value at 0 and its derivatives at 0. Okay, so what you have to find is find the derivative of f of x times g cube of x. Okay. Okay, we will try that. Maybe I will start add the chat also. Okay, great. Okay, so let's try to do it. So what we are going to use is see, if you see here, what you have is you have a product of two functions, right? So basically, this function itself is a product of three functions, and you have another function here. So you have product of functions. So when you have product of function, you use the product rule, which says that if you have two function f and g, uh, then fg prime is basically fg prime and gf prime. So basically you can take one at a time and then you multiply. So and you take the derivative of g prime here and then multiply with f prime. Take the derivative of f prime, take the g multiply with g and then add it. Okay. So we are just going to do that rule. So this is nothing but f prime of x. So if you want to find the derivative of this, so the derivative is nothing but f prime of x g cube of x plus. So now you keep the x and then take the derivative of g. So here, when you want to take the derivative of g, you have to use the chain rule. So here you have a composition of function. Okay. So you have function basically g cube of x. If you want to look, it is basically a composition of two functions. First one is the function which maps to x cube, and then the other function is basically maps x to g of x. Okay. So you are composing these two functions. So when you are composing two functions, you have to use the chain rule. Okay. So the chain rule says if you have a composition of two functions and you want to take the derivative, you take the derivative of the first function and evaluate that at g of x, and take the derivative of the second one. Okay, and then evaluate at x, and this gives you f prime of f compose g prime at x. Okay. So here when you, or anyway here you have a direct formula also, you can use it, but basically it's a composition of function. Okay. So when you differentiate, the first function you have to differentiate is x goes to x cube. Okay. So this is 3 times g of x and g prime of x. Okay. So this is what you got. Now what you do is you have to find the derivative at x equal to 0, right? You know what is the function value and the value of the derivative at 0. So you just substitute it here and you will get the answer. Okay. So f prime of 0 is 1, g prime of 0 is 0. So this part will go away. Okay, only this part you have to care about. This is f prime of 0 is 1. So this is 1 times g of 0 is 2, and you're taking the cube. So this will be 2 cube, and that will be it. So yeah, I will go little slowly because I mean some people may watch the videos etc. So I will just go little slowly so that it will be understandable for everybody. So basically, what we are applying here is one is the product rule, and another is the chain rule. Okay. So this is called the chain rule, and this is a product rule. Okay, so let us do a few more example using these things, and then we'll move on. Okay, so you might have seen the trigonometry functions, right? So you might have know the sine, cosine, etc. So what we are going to do here is we will try to find the derivative of this trigonometric functions. Okay, so what I will assume is I will assume that this derivative is known. Okay, this one has to prove, but uh, let's for now I will just assume that uh, the derivative of sine x is cos x. Okay, and then we'll try to prove the rest of the thing. Okay, so we will assume this one. Assume sin x prime is cos x. Okay, now let's try to find what is the derivative of cos x. So, so how do you find here? So if you have any idea, you can kind of let me know. And you only need this. You don't need much. You only need this and maybe little bit of. So sine pi, no, sine pi by 2 minus x. So I mean I don't understand what you're telling though. Can you repeat again? Telling sine pi by 2 minus x. No, I'm asking about what is the derivative of cos x. Okay, and see here I have even write the derivative of cos x. The derivative of cos x is nothing but minus sin x. Okay. So now we are trying to prove it. That's all. And you can assume that this derivative is there. And this might require a little bit of trigonometry, and you might have to use the uh, definition of derivative. So I'm just skipping over it. But the rest of the things one can get by just knowing this. Okay, so let's try to prove it here. So what we do is we start with a trigonometric identity that connects the sin x and cos x. Cos x equal to sin pi by 2 minus x. Yeah, okay, you can use that. That is one thing. Yeah, so we have two equations and we can use both of this. Okay, I got what you're trying to say now. Okay. So you have two ways of connecting this. One is so as he said, it's a sine pi by 2 minus x. Okay, so this is one way of doing it. And another thing is, as the other person said, it's 1 minus sine square x is equal to cos square x. Okay, so you can do both ways. Here you just you have to use the chain rule, and in this case you have to use the product rule. Well, I will for now let me take this and do. Okay, you can do with this also. It goes exactly the same. Okay. So now you take this. Now what you do is you apply the, see, one thing as you said is you're taking the square here, right? You're seeing it as a square root of 1 minus sine square x. But when you do this, see what happens is here you are introducing a new function, right? So you kind of have to do a chain rule there. Okay, so what I was trying to do is, see, I am lazy. Okay, so I don't want to do the chain rule. So let's not take the square root. Let's just keep the equation and we try to do. Okay, so what we do is we take the equation and apply the derivative on both sides. Okay, so when you apply the derivative, it is the one will go away because it's a constant. So you have minus 2 sin x, because this is sine square x, right? So you apply the chain rule, you will get 2 sin x. cos x. Because here we know that derivative of sin x is cos x, so you can use that. On this side, you will get 2 cos x. I mean, I'm applying the chain rule here. You will get 2 cos x and the cos prime x. Okay, I mean cos x prime. So I don't know what is this, but I know the rest of the thing, right? So now let's cancel out whatever the things we can cancel out. So 2 I can cancel out, and cos x I can cancel out. Okay. So this cos x I can, yeah. So once you cancel out, what you got is cos prime x equal to minus sin x. Okay, so this is what you got, but here is a small thing about canceling this. So basically when you do take the derivative of this, there will not be much problem, but when you do that you cannot simply cancel out, because what if the cos x is 0? Okay, those places you cannot cancel, and those places you might just how to do it by hand. So let's compute the derivative of cos at x equal to 0. Okay, because at not x equal to 0, x equal to pi by 2, because at x equal to pi by 2, uh, what happens is the cos pi by 2 is 0, right? So you cannot directly use that. Okay, so let's compute the derivative of cos x. So d by dx at x equal to pi by 2. If you do that, what you get is you have to apply the limit formula. Okay, so this is limit h tends to 0, f of x plus h minus f of x by h, right? So this is nothing but mm, uh, okay, let me do it. So cos pi by 2 plus h, right? And cos pi by 2, this is 0, and you're going by h. Okay, I might have to use your formula. That's, yeah. Just give me a minute. I just want to see if I can avoid it. Okay. Cos pi by 2 plus h is minus x. Oh, thank you. Is sin h, right? Sin h by h, and that will minus 1. Yeah. Okay, thank you. Say I forget this formula. So yeah. So since you said cos pi by 2 plus h, this is minus sin h, right? So you have minus sin h. Okay. So by h you take. Now you are applying the limit here. Limit h tends to 0. But we know the limit of sin h by h, as h tends to 0. That is just 1. So this will be minus 1. All right. So what happens is the derivative of cos x at x equal to, let's say, pi by 2. This is minus 1, but this is nothing but minus sin 1. Sorry, sin pi by 2. Okay. So at the places where the cos x is 0 also, you will get the same thing. Okay. Whereas at pi by 2, for example, at pi by 2, the cos x is 0. So when the cos x becomes 0, you cannot directly cancel it like that. Okay, so that's why I was doing that. How to do that? Yeah, anyway, I forget this formula. I know it is just here, but I forget it. But thank you for helping me out. Okay, so similarly, one can do the other things also. Let's say if you want to do this, maybe we'll do the tan x also, and then we will move on to the next problem. So maybe if you directly take the derivative of this, and just apply the chain rule here, then maybe this equation may be much better than working with this. Okay, because here if you take and then whatever the inside you will take the derivative, and that will be just a -1, right? And then this will be minus nx. Okay, so basically you have to use these formulas to get that. Okay, anyway, so let's proceed. So we'll take the derivative of tan also, and then we will move on to the next problem. So what we want to find is tan x, derivative of tan x. Okay. So, but what we know is that tan x is nothing but sin x by cos x. Okay. So when you have a quotient of two functions, what you do is you apply the quotient rule here. So when you have a quotient, you apply the quotient rule. Okay, if you have f by g prime, this will be gf prime. So this one has to come first. So gf prime plus fg prime divided by g squared. Okay, and again this derivative only exists whenever this function makes sense, right? Because g of x should not be 0, otherwise the function does not make sense. Okay, and the tan is defined. If you know the tan, it is not defined everywhere, right? It is only defined in particular ranges. Okay, the ranges where this cos x is not 0. So cos x will be 0 if you have pi by 2, it is 0, and minus pi by 2, it is 0. So the tan x will only be defined here. So in the quotient p minus okay, I think it is minus, sorry. Okay, okay, sorry about that. You have to put a minus there. Yeah. Okay, so let's try to solve this. So we have a tan x here. So if you take, what you will get is you divide by cos x square. Okay, and then this is g prime. So let's just look again. It's gf prime, right? So this is cos x sin prime x minus sin x cos prime x. So we just have computed what is the cos prime. Okay, so we just applied the rule for the product of this. Okay, and we have just computed what is the derivative of cos x, right? The derivative of cos x is minus sin x. So now let's use that here. So this is cos x, and then you have the derivative of sin x is again cos x. Okay, minus sin x and minus sin x. So this is cos square x. Okay, so what you get is cos square x plus sin square x by cos square x. So this is nothing but secant square x, right? So because sin square x and cos square x is 1. So this is 1 by cos square x, which is secant square x. Okay, so basically once you have done this derivative of sin x, the rest everything you can compute using the these rules together with the some of the trigonometric identity. Okay, so in some sense, if you see, right, most of the time all you have to do is you have to just use these things. You just need to do little bit here. This may not be very easy to do it. You might have to use some more trigonometry rule to prove this. But once you have this, the rest of the things follows pretty quickly. Okay. So these rules are powerful. But now we have chain rule. Later we will study two more things. One is if you have a function, and let's say you have a inverse function also, okay, then how do you find the derivative of the inverse function? Okay, so that will be another rule which will come, which is called inverse there's a theorem which is called inverse function theorem, and there is a function which is called implicit function. So those two will come. Okay, and those two together with whatever we have done so far, this is kind of more or less enough to find most of the derivative. Okay, so if you want to find the derivative, finding a derivative is not, in some sense, not hard. Okay, uh, but if you want to find the integral, that will be very hard. We will, if we when we do the, we will study that maybe later. But finding a derivative is not hard. It's just a matter of computing at least most of the derivative. Okay, so if I have something like sine hx, which is like hyperbolic sine x, then you might have to compute it from the definitions. But most of the things we will see, we don't have to do much, because these things kind of helps you to do. Okay, let's go to another question here. So this is interesting one. So here you have f of u is cos pi u by 10. Okay, and g of x is 5 root x. Now what you want to do is you want to find the take the composition of these two. So find the f composition g, and then you take the derivative of that and evaluate at 1. Okay, so let's do it. Let's first find what is the composition here. So if you find the composition, this will be cos pi by 10. But then instead of the you have this g here. So this will be 5 root x, right? So this will be 5 root x. So this is your function. Now we just have to find the derivative of this, right? So here we can simplify this if you want. And this is pi by 2 root x. Okay. So if you want to compute the derivative, you have to use the, so if you look here, this is a composition of two functions. So let's use the chain rule. Okay. So this will be, first you take the derivative of cos x, which is minus sin x. Yeah, minus sin x, and then you are evaluating at the same point. You have to evaluate at x equal to 1, of course, not x equal to 1. Yeah. Here in this case, x is equal to 1, but you are evaluating at this point itself. So you have to substitute 1 here. Okay. And then you take the derivative of whatever here. That will be pi by 2. And when you take the derivative of this will be 1 by 2. Just give me a minute. Yeah, 1 by 2, x power minus 1 by 2. Okay. So let's substitute the 1 here directly. And here also let us substitute 1 here. So sorry, this is not sin x. Sin is this. Okay, so this is minus sin pi by 2. And you have pi by 4. And 1 power, you're taking, so this is basically 1 by square root of 1, right? But that is nothing but 1. So this time you can ignore. So this is what you have, and sine pi by 2 is 1. So what you get is minus pi by 4. Okay, so let's move on. So these are the few problems you have to use the chain rule. So there's not much here, but try to practice the chain rule with somewhat difficult problem. Okay, so the practice is actually absolutely needed. The rule is simple here and all. You have to memorize it, and probably you have to practice with a really difficult problem. Okay. So I'm not doing any really difficult problem, but it's a good idea to practice 1 or 2 times. Because sometimes with practice you can able to do quickly. Okay, so let's move on to the Rolle's theorem part. So I hope you remember the Rolle's theorem. We will go with the problems directly. Okay, so you consider this function, which is the x times the square root of x square plus 1. Okay, and this function is defined on minus 1 to 1. So the question is whether this function satisfies the hypothesis of Rolle's theorem. Okay, so if you remember, yeah, so this is correct. If you remember, the hypothesis of the Rolle's theorem says what? First, you want f is continuous on the interval AB. It is differentiable on the open interval AB. Okay, and moreover, you want to have that f of A equal to f of B, right? So if you have all the three things, then the Rolle's theorem will tell you. So then the Rolle's theorem will tell you there exists a C belongs to this open interval AB, such that f prime of C is 0. Okay, so this is what the Rolle's theorem will tells you. Now we have to check each of this. So I mean, you can go in the order, but this will be easy to check here. But let's go in the order anyway. So is this a continuous function, first of all? So let's zoom in the function and see whether is it a continuous function. Okay. So if you want to say it is a continuous function, then one has to see, okay, why it is a continuous function. So let's write function and we'll try to see that this function is a continuous function. Okay. So x times square root of x square plus 1, right? So what we know is x is a continuous function. So x square plus 1, this is also a continuous function. This is also a continuous function. And if you recall, the square root is also a continuous function wherever it is defined. It is only defined for positive numbers here. And sorry, it is only defined for positive number, and wherever it is defined, it is also a continuous function, right? This becomes a inverse function of x square. So this square root is also a continuous function. So you have the this is the composition of a continuous function, and then you are taking with the product of continuous function. So this is the continuous function. And the same thing one can say for the different derivative also. So this function is differentiable. Wherever it is defined here, it is differentiable also. So these two things are came. So to do the derivative also, you just do the same thing. Each of the things are, for example, x square is differentiable. So and x square plus 1 is differentiable. When you take the square root, it's a composition of two functions, but you know you can apply the chain rule, and it is differentiable. And here also, you know, this is a differentiable function, and then you are having a product of differentiable functions. Okay, so this is differentiable also. So, but let's look at f of a, whether it's equal to f of b. So here, if you look, so x is equal to minus 1 comma 1, right? X belongs to here. So when x is equal to 1, your function will become 1 times 1 square plus 1. So which is, I don't know, my root 2, I think. When x equal to minus 1, it will become minus 1 times minus 1 square plus 1. Okay, so this is minus root 2. So if you see that the function value, I mean, at this point, at the end points, the f of a is not equal to f of b. Okay, so the Rolle's theorem you cannot directly apply. So, I mean, the reason this problem I'm asking is, see, Rolle's theorem will not be always be very useful because, I mean, although it tells you something really nice, most of the time what happens is you are having a hypothesis which is quite stronger. Okay, so that's why mean value theorem will be very useful. Anyway, let's move on to next problem here. So this is a little bit interesting. I mean, we might come back to some Rolle's theorem problem, I think, but we will do some little bit differently. Okay. Now we have two functions f and g. Both are continuously differentiable. Okay. Continuously differentiable on the closed interval a b, such that at the end point f of a will be equal to f of b. Okay. Now the question is, does there exist a point c such that g compose f? So the if you look at the composition and you take the uh, derivative of the composition, and that is 0. So what do you think? Okay, so anyway, let's try to do it here. So what we know is I have two functions here, f and g, and I know that both f and g are a continuous function, right? So if you look at the composition is also continuous in this interval. Okay. So the first property of Rolle's theorem is satisfied, which is if there were G compose. Okay. F compose G, you're telling it can be true. Okay. So well, let's see which way, whether it's F compose G or G compose F, we'll figure it out. Okay. I mean, it doesn't matter if the question is wrong. I don't think the question is wrong, but even if it's wrong, it doesn't matter. But I think this is the correct one. You will see why it is the case. Okay, so you have two continuous function. So the composition is the composition of continuous function is continuous. So it is continuous on AB. See, but here I just want to mention one thing. See, we are telling this two continuous differential function on this interval, right? Uh, so here I'm just basically I'm just assuming f is a function from a comma b to a comma b. Okay, so the thing is, otherwise the composition does not make sense, because if the G also has this as a domain, unless the F goes to here, it doesn't make much sense. So we'll just assume uh, see, this domain really doesn't matter. What you actually have to see is the composition has to make sense. Okay, so we assume that these functions are defined in such a way the composition makes sense. Okay, so then basically the G has to have some GFA and GFV. But anyway, so you just assume that the composition makes sense. Okay, so this is a continuous function. Now you're given that these are continuously differentiable functions. So basically, composition of a differentiable function is also differentiable. So you got f composition G is differentiable on the open interval AB. Okay. So now what you also have is you have f of a equal to f of b, right? So now what you do is just give me a minute. So I'm going to apply G composition with both of this, right? So then what happens? So what happens is the G composition f of a is equal to G composition f of b, right? So the composition is same. So basically this satisfy all the three properties of Rolle's theorem. See, as Sandeep had said something, he wrote f composition G. Where I wrote f composition G? Oh, sorry. Okay, it is G composition F. See, I was looking at the Sandeep command and I changed it here, I think. Yeah, so if you have the other way around, it will not work. You will just check it out. Okay. So you have all the three properties of Rolle's theorem here. Now you can just apply Rolle's theorem, right? What Rolle's theorem says is once you have all the three properties, Rolle's theorem says that there exists C belongs to the open interval A comma B such that f prime of C is equal to 0. Okay, so this is what Rolle's theorem says. Okay, good. Let's proceed further. See, such that G composition F. Oh, okay, sorry, just making the error. Yeah, G composition F prime of C is 0. Yeah. So that is what we want to prove. We want to find a point C such that G composition F prime of C is 0. Okay, I was actually, I didn't prepare this, but I was trying to think, because since we are doing the Rolle's theorem, I just want to give a place where it actually is useful. Okay. So maybe I'll try to give some example. I'm just creating now, but so yeah. So you might have this uh, polynomial function we have discussed at some point, right? So what we know is if you have a polynomial function, let's say something like this, okay, a x cube plus bx square plus cx, plus d is equal to 0. Let's say this is a polynomial function, okay? So what we know is if I have a quadratic function, not the cubic function, but just the quadratic part, then I know how to compute, right? So this much I know. Now I have a question for you. So I want to find whether it's such a quadratic function does all its roots are real. So if you have a quadratic function, it can have at most three complex roots. It's let's say we know. Okay, so that's a fundamental theorem of arithmetic, uh, not fundamental theorem of algebra, which says that if you have a nth degree polynomial, then you have at most n complex roots, right? So here what we have proved last time using the intermediate value theorem is basically if you have a polynomial of this form, then it has definitely one real root, right? So this much we know. Now the question is, can it have more than one real root? So I mean, it depends on the coefficients, of course. But I will tell you, there is some place we can use the Rolle's theorem. Okay, I will tell you here. Suppose I have a polynomial like this, and let's say if it has more than one real root. Okay. So something like this, if it has. So let's say my polynomial is something like this. So if it has more than one real root, then I have this is a root, this is a root, and this is a root. And you can see, let's call this points as A, you call this as B, and then call it as C. Okay. Then by Rolle's theorem, you know that there is a place at which that F prime is 0, right? And there is a place so basically since you have two of this, you will have two distinct root of f prime, right? So basically what it tells is if you have the quadratic polynomial, you take the derivative. When the derivative comes, you will have two different root of the derivative. So basically what it tells you is if you take the derivative, then the derivative has to satisfy okay, let's take the polynomial. Let's take the derivative of this. If you take the derivative, you will get 3 times ax square, I think, plus 2bx plus c is equal to 0. I mean, forget the equal to 0 part. Okay, so this is the derivative. So what we have is this derivative has to have a two real root, right? That means it's discriminant, whatever the discriminant of this polynomial has to be greater than 0, right? Otherwise, you cannot. So basically, this is b square minus 4ac, right? So this is 2b square minus 4 3ac. Okay, this has to be greater than or equal to 0. So this is the one condition you can just simply obtain by just using the Rolle's theorem. So basically, Rolle's theorem tells you, okay, if this polynomial has 3 real root, then it has to satisfy this condition on its coefficient. So if you look here, this is kind of like a discriminant, but for higher degree terms, higher degree polynomials. Okay, so I'm just want to tell you, okay, there are interesting things one can do with even just with the Rolle's theorem. Okay, anyway, just an aside, but if we have two such root, that does that mean that you will get it? Well, it's so. Can you give a function which has two such roots, but it does not have a, you know, yeah. Okay, can you give a quadratic function such that it has uh, you know, two roots for the derivative, uh, basically quadratic polynomial, so not quadratic, cubic polynomial, such that you have when you take the derivative, you have two real root, but it does not have a, three real root. Okay, so maybe, you take it as an exercise. I mean, I also don't know. I want us to check that. But this part one can easily say, if you have a three real root, then your polynomial, your derivative should have a two real root, and which tells you that the discriminant has to be positive. Otherwise, you cannot get it. Right? So one side at least you can say. Converse, you maybe think about it. Okay, I didn't really thought about it. So anyway, I don't want to go into uh, tangentially. So we will proceed with our problem. I'm just telling you there are something interesting one can do. Okay, maybe you can think about the converse. I will write here. Yeah, that is true. Either it has one real root or three real root. So maybe you can try to prove whether it's true. I mean, one can of course use the complex analysis and prove it, but okay. Okay, I mean, I don't know how you come up with that, but either have to put it in a graph software or something to actually see how it is. Probably, I'll check it out after the class is over. So you think about the converse. I mean, I didn't really thought about it, but yeah, I'm just telling it one application one can do. I really wants to check it whether it works, but on the other hand, we have to do the classes, right? So I will just proceed with the class. Maybe after the class is over, we can discuss about it. Okay, so let's come back to our one of okay, you have another thing. Okay, we will discuss after kind of like 8 o'clock. We will discuss whether it's correct. Okay. So you can find the function if this is satisfied. I mean, of course, you can find a function because I mean, I can directly write some function. For example, if you want to find a function, you can easily write something like that. Okay, right? Something, and then just multiply. So this will satisfy the condition for sure. What my question is, so if I have a three real root for my polynomial, then what one can easily see is that the derivative has two distinct real root, right? So I mean, basically these are the points where the derivative has a distinct real root. So this we know. My question is, if my derivative has two distinct real root, does that means the polynomial has three uh, distinct roots? So that was my question. Anyway, you can think about it, but let's proceed to. See, in fact, I mean, there is a theory behind it, okay? There is a theory behind how the roots of the polynomials exist, etc. And that actually uses the derivative. Basically, it uses the Rolle's theorem only. But anyway, let's proceed with the. Yeah, I'm talking about the converse. Yeah, I'm just talking about the converse of this problem. I mean, but see, one can do more than just a converse here. But anyway, just just keep it as some kind of application where the Rolle's theorem that you study is actually kind of useful. That's what I was trying to convey. But of course, one can do a little bit more with whatever the problem I'm talking. Okay, so let's move on to this problem. So you have a function f, which is our mod x function. Now the question is whether this function is differentiable or not. Yeah, okay, it is not differentiable. Okay, what about the other point? Yeah, it is. So, so let's compute it quickly. So you have f of x is nothing but mod x. So you want to find the derivative of that, right? Let's find the derivative. F prime at tx, let's say. This is f of x plus h minus f of x by h. Okay. And this is mod x plus h minus mod x by h. Right. So this much is okay. Now how do you proceed? I mean, see, one way to do is you just write the function here. Here it is just minus x, and here it is just x, and these functions are differentiable. All the these points you can say function differentiable. Only point is the zero, right? That is one way to do it. But let's use this definition. I just want you guys to use the definition also. Sometimes it will helpful to look at how to proceed with the definition, so you will not get scared when you have to do something. So that was the idea. So far we have done it. So let's from here, how do you proceed? So it depends on which point you are doing, right? Uh, so that was extremely important. Let's say x is greater than 0. Okay. So when x is greater than 0, what you can observe is this h is going to 0, right? So that means you have a x here and you have x plus h. Okay. So depending on whether h is positive or negative, uh, x plus h is either here or here. Okay. So it can be in both ways depending on whether the h is positive or negative. But what you can do is your 0 and x has some gap, right? So you assume that the h is smaller, because since h is anyway going to 0, why not you make sure? I mean, you just uh, see the h which are only less than this difference, less than the difference of x. Okay? So for such a x, sorry, for such a h, x plus h is always positive, right? So you have then the limit we can just directly just write the limit, which is equal to limit h tends to 0. X is 0. No, I'm just considering the x strictly greater than 0. Create numerator square minus denominator square. Okay. So you will have x plus h minus x by h. So whenever x is positive, since h is anyway going to 0, so h you can make h as small as you want, right? So just make sure that h is less than the this length from 0 to x, which is basically x. So you can, without loss of generality, you can assume that h is less than 0. This is h is less than x. Okay. So when you assume that h is less than x, then this number is positive, and hence mod is just x plus h. Okay. So this is limit h tends to 0. And now you have to look at x plus h. Sorry, I mean, just subtract it, and this will be h by h, and you can cancel out the h, and this is 1. Okay. This a square minus b square. Are you still talking about this one, mod x only? Where is a square minus b square? Multiply and divide by mod x is mod x. Okay. I mean, of course, you can do. See, there are many you can do. So I'm just using one way. Okay, what he is saying is, you have this. From here, you just, rationalize. See, denominator anyway rationalize. There's not much to rationalize. I think what he wants to do is you just multiply it with x plus h, this mod x plus h minus mod x, and divide it by the same thing. Now, you can just do some arithmetic, and you may end up doing something easier. That is what I think he's telling. But of course, I'm just estimating it, because the hatch is a limit and the hatch is going to 0. That means I can choose whatever the hatch I want, right? Sorry, whatever. Yeah, because I can choose the delta. Delta is in my hand, right? Because of that, I'm just choosing the hatch is less than x. So whenever such things happen, so x plus h will be, is always positive. Okay. So whenever the h is less than x, so this implies x plus h is always positive. So for those cases, I can directly proceed without much. So that's what I think. Might do with the other ways. Okay, and similarly you do for when the x is less than 0 also. Okay, so we did the case where x is greater than 0, and you can do the cases where x is less than 0 here. So if x is here, again choose the hatches such that have this x plus h and sorry x minus h and x plus h will be strictly greater than 0. So that for those reasons you can replace this with the minus you have to replace, and then you proceed the same thing, you will get minus 1. Okay. So that part I will leave you as a exercise. So let's look at what happens at 0. So when you look at 0, you have to look at limit h tends to 0. So mod of you have to look at mod of x plus h, right? So here this is the formula if you want to remember. Okay. I think the internet may be little bit slow. I'm not sure. Yeah, there is a little lag there. I don't know how to fix it. Okay, let me proceed here. But I can see there is a little lag. So this is mod of 0 plus h minus mod of h by h. No, mod of 0. Mod of 0 is nothing but 0 by h. So this is nothing but mod h by h, right? So and you are taking limit h tends to 0. When you have this limit, what you know is limit directly depends on which side you are taking it. Depending on the side, this limit is different. So if you take the left hand limit, this will be -1. If you take the right hand limit, this will be 1. Right? So the limit does not exist. So at x equal to 0, this function does not exist. I mean, limit of this function does not exist. Okay. So mod x is not differentiable at x equal to 0. Okay, so this we have done. So let me go to the next problem here, which is kind of similar. I just changed a little bit here, and you can see what's the difference here. So difference is instead of mod x, I'm just putting mod x plus 1. Now I'm asking the same question. So one thing what you can do is, of course, you can do the same, same argument. Whatever the argument we did earlier, you can do the same argument. All of this you can do, and you can prove. But the thing is, you don't have to do all of this. Can you give me a clever way to just to do this? We can assume that mod x is not differentiable. See, mod x is not differentiable at 0. We have just proved it, and you can assume this if you want. So I'm trying to see if there's a clever way of solving it without doing the things again. Okay, I mean, I might be saying something, but I don't know if I am actually able to. I'm actually telling what I was thinking of. So what you do is, look at mod x. Okay, mod x is nothing but f of x minus 1, right? I mean, you're just writing a different way. That's all. If suppose f is differentiable, then what happens? Since 1 is also differentiable, means mod x is also differentiable at 0, right? That is a contradiction. Yeah, exactly. So he said the same thing, right? It's differentiable as so basically, what you do is you are just taking this to the other side, and what you can observe is since mod x can be written like that, and since it is not differentiable, uh, f of x cannot be differentiable, because if f of x is differentiable, then mod x is differentiable at 0, which is a contradiction. Okay, so I'll write here. Suppose f of x is differentiable at x equal to 0, then what you get is mod x, which is equal to f of x minus 1, is also differentiable at x equal to 0, a contradiction. So sometimes to prove a differentiable or not, I mean, you don't have to actually do anything. So that was the idea. Okay. So here I'm just writing addition, but it has not really much to do with addition. You can do the other things also. Okay. But depending on something, it may or may not be differentiable. Okay. So maybe let me write another question here. I'm not writing it. So maybe I will write another question here, just to let you know that this is not always the case. Suppose if I have a function, okay, let me write the function. So f of x is, let's say, x times mod x. Okay, is it differentiable?
Sir,
Yeah.
sir, in the previous example, I think f of x is differentiable at x is equal to 0.
Why? Okay, just give me a minute.
So it is differentiable everywhere, I think.
This one.
Yes. It is not
This,
zero anywhere.
it is not zero anywhere, but that does not mean it's differentiable, right? So let's draw the graph and see. I mean, if you want a quick explanation, I will draw the graph. Okay, so this is the graph of mod x. Okay, it doesn't have to be 0 to be not differentiable. So if you want to look at mod x plus 1, so you're basically translating above it. So the graph looks something like that, and this point is 1. Okay. And here you can see there is the star V-shape tangent, right? So this is the star page. So whenever you have a star page, your function is not differentiable. So if you look at the derivative at this point, the left-hand derivative gives you minus 1. The slope of from here you can see it's minus 1. On the other side you get 1. So it's the same thing.
Yes, I got it.
You got it right?
Yes, sir.
Okay. Sometimes you can, whatever the argument I do, sometimes you can do it. See, I think the video is a little lagging. But anyway, let me proceed and maybe I will try to log in back again. Okay, so let's go to the this problem. Here, what happens is instead of addition, I'm just doing the product. Now, what about this one? Okay, here I cannot that argue like this. If I want to argue, then this has to go downwards. But then this will become, you're multiplying something at 0. If you want to find the derivative at 0, then you're multiplying at 0. That makes no sense. Okay. So let's take what we know is other than 0, this function is differentiable, right? That you prove it. Okay, it is easy because other than 0, you can write that f of x as either x or minus x. Then you have two possibilities. If I am writing function directly, I can write the function. This is x square if x square if x greater than 0 minus x square if x less than 0. 0 if is equal to 0, right? And now minus x square. Yeah. So this is my function. Okay, and it's not very to verify that other than 0, this function is differentiable. Okay. But let's look at what comes at 0. Then I have to compute the limit h tends to 0, f of x plus h minus f of x by h. Right? So this is nothing but this is x. Sorry, x is 0. So this is h mod x by h. Okay. And you have to limit as h equals to 0. This is nothing but other. I can cancel these things. So this is the limit of h goes to 0 mod h. But this is 0. Okay. So this function limit exists. Okay. So whenever you have some linear combination of this. So if you have linear combination of many functions, linear combinations I'm just telling some and multiply with the scalar. So if you have a f1 plus b f2, something like that, let's say. Okay. Then I mean, then one can do if one of the functions is differentiable, we can plot like this. But in general, you cannot directly do this. Just want to give a caution that just because this is not differentiable does not mean a product of two function is not differentiable. Okay. You don't need both of the function to be differentiable for the product to be differentiable. What you know is if two functions are differentiable, then the product is differentiable. Okay, but the converse need not. I mean, need not to be. I mean, you don't need the functions to be differentiable to make the product to be differentiable. Okay. Uh, so there is a comment. So let me check that what it is. So you're asking if f of x is 0, g is continuous but not differentiable. If is continuous, if g differentiable. Okay. Yeah, I mean, I understand the question, but I have to think. I think. Just give me a minute. We'll see. G is continuous but not differentiable. Do you know that f is continuous? Okay, f is continuous. Not differentiable. F is continuous. Okay. No. When but you don't have that f is differentiable, right? Basically, you have to continuous function only. In general, I don't think it will. But I am not able to directly give a counter example. Okay, you want me to write the limit? Okay, let's see what is the limit. So I want to look at fg. So this is the limit. H tends to 0. Fg of x. I mean h of x plus h is fg of x by h, right? Okay. And what you have is uh, f of x is 0. So this term will go away. This will be 0. So what you have is fg x plus h and h, right? But I don't know any reason why it has to be true. See, I mean, if you want, I can give an example. Maybe okay, I got one example. I will tell you. So, if G is continuous or not differentiable, okay. Okay, I don't know the example of G is continuous but not differentiable, but I can give one example. Maybe you take this. Okay, take both F and G as just this, and then you try to verify. Yeah, I think this might help if you want. Okay, think about it and let me know if it works for you. Okay. So here f of x is 0, whatever you said is there, and g is continuous. Well, it's a differentiability x, and f is also continuous at x. Okay, but this function is basically mod x, which is not differentiable. So I mean, if you take f times g, that is basically just mod x, and we just assume that it is not differentiable, right? So. Okay, so let's move on to the next question here. So just want to see that internet is working properly. Okay, so let's move on to the seventh question. So here you want to find the critical point of this particular function. Okay, so let's try to find the critical point. So critical point is what? Critical, I think. Okay, Advait, we will discuss, at 8 o'clock. Okay. Uh, yeah, at 8 o'clock we will discuss. I think it will work if you could. Okay, we will discuss at 8 o'clock. Okay, I just have to think a little bit and then we will come back to you. Okay, so let's try this problem. Uh, so here you have a critical point of, you want to find the critical point of this particular function, right? Okay, so we have this function. What is the critical point? Critical point is the point C such that f dash of C is equal to 0, right? So let's take this function and try to find the derivative of this. So the derivative is 3x square plus 2x minus 2. And I want to find this derivative. I want to find where it is equal to 0. So that is basically you just have to solve this equation, right? Yeah. So this, if you want to solve it, what you get is so minus 2 plus or minus. So b square is 4 minus 4. So this is a into c, that is 6 by 2a, right? Okay, 2.3. So this is these are the critical points. And maybe let's simplify a little bit. This is minus 2 plus or minus square root of this is 28. So that is 7 times 4. So the 7 will stay here and 2 will come here, divided by 2 times 3. Okay. So this is nothing but minus 1 plus or minus root 7 by 3. Okay, so these are the critical points. So basically, to find the critical point, you just take the derivative and equate it to 0. Okay, and then you can see this is a polynomial function, so we are using the quadratic formula. If there is some other function, then you have to find at which points that it is equal to 0. Okay, so let's okay, it's right. Yeah. Okay, why it is 3. Yeah, okay, I think it's right. Okay, so let's do another problem. So we will now we come to the maxima and minima problems. So here you have a function here, let's say, and this function has a maxima and a minima. Now the question is, okay, what is the maxima and what is the minima? Okay, so this is minus. Sorry, there's a minus here. Okay. So to find the maximum minima, there is two tests you can use. First, what you have to do is, there is a theorem which says that if there is a maxima or minima, so this implies okay, at x, let's say if you have maxima or minima at x, then this f prime of x is 0. Okay, so it's the converse is not true. If you have a critical point, that does not mean it has a maxima or minima. What we know is, if we have maxima or minima, then it is a critical point. Okay, so and then you have two tests here. Either you use the first derivative test, or you use the second derivative test. Okay. So I think it is done in the class, but let me just recall it. So the first derivative test is the following. So suppose if this point x, and it has a, it's a critical point. Okay, so let me draw a graph here. So you have point x and it's a critical point. So something like that is happening here. Okay, then what happens is, if you look at the local neighborhood of this, the neighborhood of the point x, you can see that this tangents here. So if you look at the tangent, so this, the slope of this tangent is positive, right? But as it goes down here, the slope of this tangent became negative, right? So if you look, the slope uh, is kind of increasing here. I mean, it kind of decreasing. So it is positive. Uh, you can see the slope is keep decreasing. So whenever you have something like this, and the slope changes from positive to negative. Okay, so what I mean by positive and negative, so if you look at the line here, the slope is basically tan of this theta, and you can see the slope of this is a positive. Okay, and if you have a line like this, then the slope is negative. Anyway, I mean, I assume that you know what is a slope. So here you can see the slope is positive and it is becoming negative here. Okay, so whenever the slope changes from positive to negative in a neighborhood of this, okay, then this point x must be a maxima. Okay, so slope changes from positive to negative, then you have a maxima. And similarly, let's say I have a, well, see, whatever I'm doing here, it's not a proof. Okay, I just want to tell you, this is not a proof. I'm just giving the intuition. I mean, it works for this graph, and any graph which has a maxima, you can see it. But it's not a proof. For proof, you have to do the proof. But I'm not going to do the proof here. Okay. And let's look at another function here. Okay, so you have a function, let's say something like this. Okay, and you look at around this point x here. Okay, if you look at around this point x in a small enough neighborhood of the point x, what you can observe is the slope here is negative, right? And here it is negative, here it is negative. All these points, the slope is negative. But as it goes here, the slope became positive, and at this point, the slope is 0, right? So the slope moves from negative to positive. So whenever the slope moves from negative to positive, okay, or basically, or what happens is the derivative in the right side. So derivative is basically the slope, right? So derivative on the left side is negative, on the right side it is positive. So, or you can say the derivative also, not necessarily slope. So derivative moves from negative to positive as you move in this direction. Then you have a local minima. Okay, and you have a second derivative test. See, but there exists a case where it goes to 0, but then it will not stay at 0. I mean, it will not go to negative. So for example, you have a graph. Maybe I'll draw one more graph and then I will stop drawing it. Okay, so let's say I have a graph like this. So here, if you observe, what happens is your slope is positive. Here it became, it is still positive, but the slope is less. And at 0, it became 0. Again, when you go up, the slope is not getting negative, but it again became positive. Okay, so the slope, if you draw, the slope will be positive. It comes to 0, and then it goes up, right? So this function is, let's say, x cube by 3. I mean, I'm just putting the 3 so that this function became x square. So if you look at the derivative is x square, right? Derivative of this function. So you can see the slope comes, it never goes down, it just goes up. So such a point will also has the derivative is 0. Okay, but this is neither a maxima nor a minima. Okay, and such a point exists, and those points are called and this point is actually called point of inflection. uh, because there is something little bit kind of happening here. So I will tell you what is a point of inflection, but let's go back here. So this is the first derivative test, what it is about, and you have the second derivative test, which goes like this. So now if you look at so how do you see the second derivative? Second derivative is you see, if you see the first derivative as a rate of change, you can see the second derivative as the acceleration that is happening. Okay, uh, how fast your curve is accelerate or decelerate. Okay, and so here if you look here, uh, here the slope is steep, right? So here the slope is steep, but it's kind of uh, keep decelerating. So the slope is keep going down and down and down, right? So if you look at the second derivative, so second derivative is less than or equal to 0. So basically what happens is your slope start positive, but then the slope is keep on going down, right? It's kind of the slope is deaccelerating here. So whenever the slope is keep deaccelerating, so basically it is its value is going down, then you can see there is a maximum. There's a maximum here. And similarly here you see the slope here is increasing. So if you see the slope is like this, and here it's kind of accelerating to be positive, right? So the slope changes from uh, positive to negative to positive. That means your slope, the rate of change is kind of increasing, right? So slope is increasing at the acceleration is increasing here. And when such a thing happens, so that is basically f double dash of x is greater than or equal to 0, then you will get a minima. Okay, so when you have the point of inflection, or there is another little bit more, this kind of thing is called, I think, uh, I forget, it's either concave or convex, I forget it. Yeah, but anyway, I will not go into that. Okay, and here you see the slope is it accelerate, the slope kind of goes down here. Just give me a minute. Yeah, it goes down here, but then it kind of goes up again. So because if you see the acceleration of this curve is very high. But anyway, the second derivative is a little bit hard to imagine, but yeah. So you see it as how the curve is accelerating. So what do you mean by accelerating? I'll tell you. See, this curve is also increasing, okay? But this curve, okay, I will draw maybe two curves. Then you might know what I'm trying to say by accelerate. So this curve is increasing, of course. But if you look at this curve, okay, not irrigated line. Okay. So if you look at this curve, both are actually increasing, but one of them is increasing at a increasing rate, right? So that's what I mean by accelerating. So this is accelerating more than this curve. Okay, suppose if it goes like this and if it comes like this, that means it is accelerating, but then the acceleration became less. But anyway, uh, yeah, so that is what it is. So let's do the first derivative test or second derivative test. Second derivative test may be easy for this. So let's proceed with the test. If you have any doubt, you just let me know, okay? Because I did some, I want to say something in some geometry or whatever it is, but I hope I didn't confuse you. If you have any issue understanding whatever I said, it you just let me know. I will repeat again, or I can try to customize whatever the place you didn't understand. I can try to explain. Okay, so let me take the function here. and we'll try to multiply and see. Okay. So you have the function. So now the first job is to find the critical point, because we know that if maximum minimum exist, then it's a critical point. So if you want to find the maximum minimum, so let's look at the critical point and see what are those. So the critical point here is if you take the derivative of x, this is x square minus 4x plus 2, right? So this is a 4 plus or minus square root of b square is 16 minus 8 by 2. So this is 4 plus or minus root 2 by 2 root 2 by 2. Okay. So this is basically 2 plus or minus root 2. Okay. Now we got 2 points here. So this is basically 2 minus root 2, and this is 2 plus root 2. So now the question is, okay, at which point it's a maxima and which point it's a minima. So what you do is you compute the second derivative of it. But here the second derivative is easy to compute, so you can take the second derivative test. Of course, one can do the first derivative test also. But here we do the, let's say we do the second derivative test here. Okay, so let's compute the second derivative here. So let me just zoom out a little bit. So f prime of x, here is my first derivative. So this is 2x minus 4, right? Okay. And so 2x minus 4. Now what you have to do is you have to substitute these points and see what happens. So let's substitute 2 minus root 2 here. So if you substitute that, that will be a 4 minus 2 root 2 minus 4. Okay, so this is minus 2 root 2. So at this point, at the point that 2 minus root 2, you have the second derivative which is negative, right? So that means this point is a maxima. So this point is a maxima. Okay. Now similarly, let's look at the other point. So this is 2x minus 4. Now substitute 2 plus root 2. So this is again it's 4 plus 2 root 2 minus 4. So this is 2 root 2. And this is greater than or equal to 0, right? So at this point, the second derivative is greater than or equal to 0. So this point is a minima. Okay. So that's all. I mean, it's not very hard to compute. All you have to do is find the critical point and apply either the first derivative or second derivative test. Only issue that happens is when the second derivative test will fail if you have sorry, this is not exactly less than or equal to 0, it's strictly less than 0. And here also it is strictly greater than 0. Okay, whatever I write here. The problem happens when the second derivative test, f dash of x is equal to 0, then you cannot do anything. So, I think I made a serious error here. So this is not greater than, so you, okay, for maxima you need strictly less than 0. Okay, for minima you need f prime of x to be strictly greater than 0. Okay, whenever you have f prime of x is equal to 0, you will not get any information actually. Yeah, yeah, as you said, it's actually strict inequality. When you have f prime of x is equal to 0, you cannot get any information, because here you take this example. Okay, so take this example here. At this point, if you compute the second derivative at the 0 is 0. Okay, but you can see here this neither a maxima nor a minima. Okay. So yeah, that was the thing. So in general, you cannot say anything. Okay, so let's proceed with the problem. I'm just thinking a little bit. Yeah, another thing is if f double dash of x is 0, that does not mean the point is always a point of inflection. That also I just want to repeat. So I will give one example to justify that that is also not true. Okay. So you take this example. Hmm. So f of x is x cube or x cube by 3. I mean, you can take it, let's say x cube. Uh, if x is greater than or equal to 0 or the minus x cube if x is less than or equal to 0 or less than 0, doesn't matter. Okay, so if you want to draw the graph, how the graph looks, it's basically you have uh, let me just look here. Here you have this function, and I'm taking the minus. So basically, I'm just my function will look something like that. It's not exactly the parabola, but it's a little bit more cylindrical. I mean, it goes more faster than the parabola, something like this. Okay. Okay, but anyway, I mean, you have this. Basically, you are flipping this thing to above. Okay, you just reflect it along this x-axis, then you will get the x cube function. Okay, now I mean you can check the only problem at which the derivative has a problem is basically at 0, and you can check at 0 that this function is differentiable. Okay, if you want, we can just check. So f prime at 0 is nothing but what is this? This is a h cube, right? So yeah, it depends on whether h is on that side or this side. So this is a h cube by h if h is greater than or equal to 0. So you have to find the limit here, but function is a little bit different. And it is a minus h cube by h if h is less than 0. But in either case, you can cancel out because h is not 0. So what you get is here you get h square and here you get minus h square. And then you find the limit as h tends to 0, right? So this is basically 0. This is 0. Okay. So this is what you will get. So the derivative exists at 0 and which is actually 0. And you can compute the second derivative also. What you can see is the both derivative exist. Okay. Uh, both derivative exist, and if you look at the second derivative at 0, it is 0. But this point is not a point of inflection, because if you look and if you draw the graph, you can clearly see that all of these numbers are positive, right? If you want, you can directly do it, but either you can draw the graph or you can prove it, just use the algebraically, analytically you prove it, but the graph looks something along this line, something like this. Okay, so x square may be a little bit wider, and this will be yeah, the acceleration is kind of, so basically you draw the x cube and then you flip this part up, so it looks something like this. Okay, and the thing about it is this point is a minima. Okay, it's not that second derivative is 0 does not necessarily mean it's a point of inflection. What it tells is if the second derivative is 0, then we don't know what is going on. Okay, so that was the only thing. It does not tell you anything. So yeah. But on the other hand, if you look at the first derivative test, I think the first derivative test works. Okay, why? Because here the slope is negative, and here the slope is positive. Okay, so the slope moves from negative to positive, and the first derivative test works here. Okay, for this problem, first derivative test works. Okay. Even though the second derivative test is sometimes easy, it will not always work. Okay, so that's just I want to give a note there. But the first derivative test more or less works here. Okay. Okay, because the first derivative, if you compute the first derivative, is nothing but basically f prime of x uh, is nothing but basically x square if x is greater than or equal to 0, or x square by 3x square. This is minus 3x square if x is strictly less than 0. So here you can see the it goes from negative to positive, right? So first derivative moves from negative to positive as you move in this direction toward, I mean, 0 is here, and as you move in this direction it goes from negative to positive. Okay, so the first derivative test works, and you can see that this is a minima, but the second derivative test does not work. So just want to mention that sometimes, yeah, that is the thing. Okay, I will just check how much time we have. We have some time, so we can proceed with it, I think. Let me just check if I have something interesting to say. Okay, anyway, we can at least do two questions, so we'll proceed here. Okay, so at which point the local maxima occurs for this function? At which point the local maxima occur? That was the question. So let's try to find. So if you want to find the local maxima, the first thing you have to find is what is the critical point, right? So let's try to find the critical point. This is, I mean, you can compute parallelly, and you can let me know if you got the answer. Okay, so look at the f prime of x. So here you have to apply the product rule. So this is 2 by 3 x power 1 by 3. So here I am using the formula derivative of x power n, okay, d by dx of x power n. This is nothing but n into x power n minus 1. Okay, so I'm using that formula here. So basically it will be 2 by 3 minus 1, and you just compute this is minus 1 by 3 by 3 5 by 2 minus x plus now I keep this term and differentiate this term. This will be x power 2 by 3 minus 1. Okay, and I want to set this as 0. See here, if you look, this is not a polynomial function, so you cannot use minus b plus or minus b square minus 4ac by 2a. So we have to do something else. So let's see. So this is a 2 by 3 into 5 by 2 x power minus 1 by 3. Okay, so this is this minus 2 by 3 x power 2 by 3. So I'm just multiplying this and this, and that will gives me this minus x power 2 by 3, and this is equal to 0. So let's that in place what? So I can cancel this to part. So I will get 5 by 3 x power minus 1 by 3. I will take these terms to the other side. Okay, and that gives me, so here you have this 2 by 3, and there's 1 here, and then you just add it because these terms are common. So if you do that, you will get 5 by 3 x power 2 by 3. Okay, so this 5 by 3 get cancelled. So this x power minus 1 by 3 equal to x power 2 by 3. X equal to 0 is the local maxima. X equal to 0 is local. X equal to 1 is a local. Okay, x equal to 0 is a local. No. Okay, we'll see. So this will be, I mean, I will take it to the other side. Okay, take it to the other side, you will get x power minus 1 by 3. plus x 2 by 3 equal to 0. So what we do is we have this equation. We just see this is a what? This is a minus cube root, right? This does not make sense. Just give me a minute. Without it running. And the function I think is not differentiable. Yes, yes, yes. That's what I also got confused now. How do you differentiate at x equal to 0? Yeah, the function will not differentiate at x equal to 0. So yeah, at x equal to 0, probably we have to, kind of things separately. So let's leave the point x equal to 0. Other than x equal to 0, we'll proceed, okay? So from here, I just multiply with the entire thing by x power 1 by 3. So if you do that, you will get 1 plus x. 3 by 3 is 1, which is equal to 0. Okay. So I get x equal to minus 1. Yeah, am I right or I missed something? Yeah, I missed something. So this is minus minus. So x is equal to 1. Okay. So the critical point is x equal to 1. And then at this point, you have to find uh, what is happening, right? So let me go again here. Where is my point here? So this is my function and this is my derivative, right? All I'll take here, let me see if I have some different thing. Okay. Okay, so this is my derivative. So I will take my derivative here. Because I just want, I mean, this is the critical point, right? So this is the critical point. And I have to either use the first derivative test or I have to use the second derivative test. So let's try to use one of the tests. So this is my first derivative. This is basically f prime of x. Okay. So let's see if we can use the first derivative test quickly or you have to go to the second derivative test. Okay, so let's cancel it and see. So this is 5 by 3 x power minus 1 by 3 minus 2 no minus 5 by 3 x power 2 by 3. Okay, so this is my function and yeah, I think maybe the second derivative test may be easier. So let's just directly go to the second derivative test. So this is 5 by 3 minus 1 by 3. So in x power in x power n minus 1, right? So this is x times plus 1 if you put, that is 3 would be 3, I think this is correct. So if you put 1, so that is basically 3 by 3. So that will can no my x minus 1, so this is 3 by 3. I think it is right only. Minus 5 by 3 into 2 by 3. So and then I have to compute x power 2 by 3 minus 1, which is minus 1 by 3. Okay, so that is good. Now I have to evaluate so this is my second derivative, but I have to evaluate at 1. So this will be 5 by 3. So this is minus 5 by 9. Okay, so here you put 1, then this time is just 1. Minus 10 by 9. So just a minute here. Yeah, minus 10 by 9. So here you can clearly see that this time is strictly less than 0. Okay, so thus at x equal to 1, you will have a local. You will have so local maxima. Yeah. So at the point x equal to 0, what happens is your function is not differentiable, right? So when your function is not differentiable, such points are also called critical points. So your point is said to be critical point if either f prime of x is 0, or at the point it's not differentiable. Okay, so then at the point at which x equal to 0, one has to actually check what exactly happening. So at the point 0, it is 0. When it is not 0, then what you can say? So first derivative test. No, we cannot apply the first derivative test. Can you still apply the first derivative test? I don't know. I think if it is a critical point, you apply the first derivative test. I mean, when the derivative exists, at least that much I know that one can apply the first derivative test. When the derivative itself does not exist, can you apply first derivative test? I don't know. So that one has to actually see what happens there. One has to look at the local neighborhood of this to see it. Yeah, I'm not exactly sure about the first derivative test, whether can you apply for this. Maybe I will just check if you give me a minute. I mean, I will just check it and just to make sure that it is right. Yeah, I think you can. It will give the increasing and decreasing. Yes, yes, yes. So I think you can apply the first derivative test to that also. The second derivative test can you apply? Yeah, second derivative test also you can apply. Okay. So here is your first derivative, right? So let's look at the point x equal to 0, and let's try to apply the first derivative test here. Is this is the correct one? Yeah, I will take this one instead. Okay, so this is the f prime of x, and let's apply the first derivative test. But before that, let's simplify a little bit. This is 5 by 3 x power minus 1 by 3 minus and here we have 2 by 3 x power minus sorry x power that's 5 by 3, right? And that is 5 by 3 x power 2 by 3. Okay, so this is what you have now. And the cube root of negative number is a negative number, right? Yeah. Yeah, so cube root of negative number is a negative number. So at 0, you look at 0, and if you have a negative number, let's say, so the cube root of a negative number is a negative number. Here also the cube root of a negative number is a negative number, and then you are taking the square, right? So this is a positive number. Uh, Let me just make sure that's a positive number. Negative number is negative number, and then take square. Yeah, so this is a positive number, okay? And this will be a negative number. So this whole is a negative number. So this part is a negative number. This part is positive. And so as a whole, if you look, so this is a positive, and you have minus, right? So the total is a negative number. So what I was telling is the cube root, if you take a cube root of a negative number, that is a negative number. And the cube root always exists, right? I mean, there's a cube root exists in real. I mean, at least one of the cube root exists. And does one of the cube root always exist? Yeah. Yeah, I think one of the cube root always exists. And then you got it. That's all. So if you want why the cube root exists, I mean, I can prove if you want. Maybe I'll prove here. See, if I just look at x power 1 by 3, no, this is cube root right here. I mean, yeah, cube root always exists. I mean, I don't think there's anything to prove. Yeah, so maybe I'll just write a little bit simplified if you want. It's basically 5 by 3, 1 by cube root of x minus 5 by 3, 1 by cube root of x whole square. Okay, so that's what I'm telling. This is a positive number. Whereas cube root of, whenever I look in this direction, this is a negative number. But when I take the square, it became positive number. So this whole is a negative number, and this is also a negative number. Okay, so in this part, your slope is negative, and you can check in this part, that is a positive number, and this is a positive number, but I have to subtract two positive numbers, so that I don't know what it is. No, this is not 1 by 3, right? It's not 1 by 3. So this will be root of x square. Okay, so let's assume the x is a cube root in the numerator. It's not increasing. Yeah, cube root in the numerator. I mean, I made some error here, but anyway. So this side, let's look. So this will be again 5 by 3. And here you have 1 by cube root of x. So now you assume the x is positive. So you are looking in this direction where x is positive. Minus cube root of x whole square. And we want to see whether this number is positive or not, right? So let's try to do a little bit. And this is basically 5 by 3. 1 minus cube root of x square times cube root of x by cube root of x. Okay, so I'm just computing it here. So here I have cube root of this will become just x. So this is equal to 1 minus x by cube root of x 5 by 3. Okay, so this is what we got whenever x is positive. Okay, but here you observe that as long as that x is less than 1, so you have 0 here, and whenever the x is less, here you have 1 here. So you have 0 and here you have 1. So whenever your number is between 0 and 1, this term is positive, right? So positive if x is less than 1. Okay, and when x is equal to 0, this term is 0 again. Sorry, x equal to 1, this term is 0. So here you have positive, and at this point it is again 0, the slope is 0, because we have already seen this as a critical point, and here it became negative. Okay, so this became, so this, sorry, here you have a maxima and here you have a minima. Okay, so it changes from negative to positive, so you have minima. Okay, so those are the two critical points. So there are other critical point. X equal to 0 is also a critical point. Okay. Okay. So let's move on to the next question. You can the cube root is yeah, you can just simply taking it here. Okay, so let's compute this. So the reason we are coming to the inverse functions, and which we have done in the lecture also, is because we are going to, so if I have function which is differentiable and it is invertible, let's say, okay, then I might be interested in knowing what is the different, sorry, derivative of f inverse, right? So that's why we are studying again, coming back to inverse function, because we are going to say what is the derivative of inverse function. Okay, that will be in the next week, I think. So now we have a problem here, which is this function, and I want to find the inverse function of this. So yeah, so how do you find? One way you do is you just compose these two and check that this is the inverse function. Okay, so that you can do it. So I will just tell you some way where you can just see it step by step. So you look at this function. Okay, so this is basically e power 3x plus 2. So basically it x goes to e power 3x plus 2, right? So this, if you want to look, it x goes to first, x goes to 3x, and now it goes to 3x plus 2, and then finally you are applying e, right? So at each point, it is a basically composition of the function, right? So if you, let's say this function is a multiplication, this function is addition by 2, and now you are taking the exponential. So you have three functions, and the whole function, this is a composition of these functions, right? So when you have something like that, and you want to go for the inverse, what you do is you take the inverse of this first, then you take the inverse of this, and then you take the inverse of this. Okay, so this is something like if you have let's say you have a leg here, and in the leg, first if you put a shoe, sorry, first you put the socks, and now you put the shoe. Okay, but when you want to remove it, you first remove the shoe, and then you can remove the socks. You cannot directly remove the socks first. So this is a very it comes everywhere. It's just a standard idea that when you compose like this and you want to take inverse, you go in the reverse direction. So what you do is every step you take the inverse, and that will be the inverse of this function. Okay, so let's take here, we have y. What is the inverse of this function? So the inverse of this function is basically log y, right? So this is log y. So here what I did is I'm taking just the exponential. This function just exponential. So when I come back, I'm just taking logarithm. In this one they are writing ln instead of it's a natural logarithm. But one thing here you can observe is, see, if you here you have to look at the domain properly. So the exponential function, which x goes to e power x, it has, so let's look at how it looks. So the function kind of looks something like this, right? So the codomain of the function is basically 0. It's not 0. It's open 0 uh, to infinity, right? So the inverse image domain starts from open 0 to infinity. That's very crucial because here the x has to be greater than or equal to 0. Okay, because the domain is the when you go with the inverse function, the domain has to be from 0 to infinity, so which is same as this. So these two are the same. If you look, only difference is this. So this is not correct. Okay, and I mean, of course, you can just cancel out all of this. Okay, so because the domain is wrong, so you can cancel out all of this. But anyway, so let's get the inverse function also. Okay, so this part is done. Now from here, we go further. So here what I did is, whatever the term here, I'm just adding 2 to it, right? So the inverse of that is basically I'm just subtracting 2. ln of y minus 2. Okay, so so far that is good. Now I look here, what I did is I'm multiplying by 3 here in this step. So the inverse of this is I'm going to divide by 3. So this is ln of y minus 2 by 3. Okay, so that is your inverse function. And see, and all the other steps, there is no restriction on the domain. Only when you go here, there is a restriction on the domain. So rest everything works. So I'll just erase it a little bit. ln of y. So you go step by step like this. When you take the inverse, you come in this direction. Okay. So this is the one, and let's check if it is there. Yeah, it is there. So this is correct because of the domain consideration also. You have to take it. Hey, by the way, Advait, when you solved it, did you solve like that, or you had a better idea to quickly do it? I mean, you can let me know in the comments. No better idea. Okay, we will discuss that and see how to do it. So because I'm interested, because once you see it, you just told the answer. So I just either you have to be very quick or there has to be better idea. So I'm just interested if there is a better idea. Okay, since the time is gone, we will stop now and we'll meet in the next class. We'll see you.